Let me move on to chapter 5 on the Morgan. The first section is a review on the conditional vulnerability. So, let me give a application. So let's recall, okay, given an event A random variable y, discrete here, so discrete. The conditional expectation. Sorry, I should say a conditional distribution y given A is a random variable with PMF. Y given y, condition of A. Alright, with PMF, this is a random variable with PMF. Probability of y being in a y condition on A, and the conditional expectation. Expected value of y condition on A is because of the summation of y multiplied with the probability big Y is the little y condition on A. Okay. I'm sure you have seen this, and we have been doing this for a while, and it shouldn't be anything surprising. Let me denote the indicator function 1a x is equal to 1 if x is in A and 0 otherwise. Then we have a couple facts. So where's the fact number mentioned? Fact number 1 is the expected value of y multiplied by 1a. Okay. By the definition, so by the definition, it's a summation on y, probability of y given y, intersection with event A occurring, right? And based on that definition of the conditional expectation, this is the same thing as saying y make y given y condition on A, probability of A, which is equal to expected value of y condition on A and multiply with the probability of A. observation, if I have a collection of AK, and collection of events, AK, that joint and home, and the union is the temporary space. The union of AK is the whole concrete space. Then what do I have? Then I have expected value of Y. It's just the law of probability. I've seen this already. Summation of Y equals 1 K. Which is equal to the summation of K. So value of Y 1 and K. And which is equal to the summation of expected value of Y condition of K multiplied by the probability of K. Of course, for everything here we have to assume expected value of Y is finite. So I guess I have to assume assume expected value of the absolute value of Y is really finite. And so I can talk about the conditional expectation. And the third fact is about the convexity. Third fact is if f function phi is concave, is a convex function. In other words, it is a concave then expected value of phi of y conditionally. This expected value is always greater than expected value of so the phi is outside. Phi expected value of y conditionally. So, for instance, think about like a 5 in a, say, it's a square, for instance. Alright, so these are just the facts that I am just trying to recall, just in case. Now let me move on to the next definition. Alright, so this is something I would say kind of new to you. So suppose y, I guess I want to call y is based on z. So z is just that. Infinite. Okay. Then z is all couple word adapted. Okay, adapted. Which also known as measurable. Which also known as predictable. I'm sorry, not predictable. This. With respect to a random variable x, alright, if for all x, I have z conditional base of x. So these constant, where I denote AX is when X is equal to 1. Alright, so based on the definition above, Z conditioned on this event is a random variable. However, if for X, this random variable is simply a constant, then we're going to call Z to be adaptive or measurable. With respect to X. That means if I tell you the value of the X, then you will be able to tell the value of the Z. This is I would say this is kind of like a very, very, very basic, I would say, very simple version of the so-called measurable. If you take a course in analysis or probability, advanced probability, it will give you more complicated definition. But here, for the sake of the chapter, we use this definition. For instance, let me give, so for instance, let's give an example to illustrate an example. Okay. X is adaptive with respect to that means, what does that mean? It's clear that suppose if I tell you X is equal to little x, what is the value of this random variable? Little x? Because if you already know this, then this has to be x. Right? Which is a constant. Yeah?
Is this the same as the notion of a random variable is sufficient for a random variable?
It's sufficient? No, not that one. You're confusing with the statistical sufficiency. Not the same.
Because in here I see that if you know X, then you know everything about Z.
Well, that one is, that's kind of like I would say, you can have a good point. If I tell you, you have a good point. Well, I am tempted to say no, they're not the same thing. That's because in the sufficiency, if I tell you the value of that, distribution, then you will be able to determine the distribution of the whole family, right? Like suppose if I tell you C is equal to suppose U is equal to U, and the distribution of the collection, say, distribution on U is determined. But then that's, well, I would say but here I would say, no, they're not the same thing, because here, based on this definition, that means this has to be a constant. But that can still be a random variable. So I don't think that's it. But somehow they look very similar. True. Yeah. Okay. All right. So moving on. So 2. So for instance, another one could be the constant C is a constant, and C is adapted to X. This because if I have C being a constant and conditioning or whatever on X, C is still a constant. So C conditioned on X is always C, constant, so it doesn't really go anywhere. Another example could be, for instance, so if Z is, I guess, also let me something for instance, so X squared, for instance, is, that is because if I tell you the value of X, then you know the value of X squared. The same with X squared. Constant. Right? And so on. What else can I say? So now, so if Z is Z is adapted to X, then for any function after Z, then so is so for any is because if I tell you X, the value of X, and Z is a constant, then that Z has to be constant, basically. Because Z condition on is a constant, imply that Z is so note here, if Z is adapted to X, then we have Z condition on X is a constant, and that is supposed to be equal to the expected value of Z condition on X. This is clear because if that is a constant, then the mean is itself. If it's a constant, then the mean is itself. So that's why we have that note here. Okay. All right, so let me move on to the conditional exploitation as a random variable. So the next definition. Okay, so suppose y is a random variable. So the value of y is finite. Then let y star be a random variable satisfied following this could be thought as the following. You have a random variable y outside here. To think about this is the space for x. Okay. You're gonna look into this kind of abstract plane. You project y into this. This would be the y star. Okay. It's something like this. Something like that. Will be clear in a moment, but for now, think about it that way. Okay. All right. Then, then y star is called the conditional expectation of y given x, and it is typically denoted as expected value of y conditional. This is kind of like a generalized version of the conditional expectation conditioning on an event. Here, it goes like this. I condition on a random variable x, okay? And so this is a random variable satisfying these two properties. So, let's see if I have the sample illustrate.
So y star is unique. So if it satisfies those two properties, then it's uniquely circumscribed. There's only one random variable, y star.
I'm going to write it. All right, yes, indeed. So I have a theorem. From what? Y star is unique. In other words, suppose I have y field satisfies also what do I have the label? I guess one labeling maybe A and B. Okay. Suppose y star satisfying A and B, then probability y star is the same as y field. Second, I always have expected value of y star condition on AX. Same as expected value of y condition on AX. And as a consequence, we have expected value of y star. Same expected value of three, linear combination. Expected value u plus v condition of x is expected value of u let me write down all the fields. Okay, so if I have y is independent of x, right? Then y condition of x, this random variable is simply constant. And simplify. If I have w is adapted to x, and then I have then w is the same as w condition on x, and I have conditional expected value w y condition on x. This random variable is the same as w condition on x. Okay. And what else? So this is 5. I have. And then the last part, I guess I'm going to say that's consequence. Here. If C is a constant, then I have expected value of C1 condition on x is C, expected value of y condition on x. Okay, so 1, 2, 3, 4, 5. And last property. It's the following. 6. Okay. So conditional application on conditional max. Minimize the following quantity. Y minus y, what do I want to call? So I guess I want to call z squared among the z adapted to which explains the picture that I have above there. So you have a y outside, then you project the y onto the, think about the space of x, and your information there is your best guess about y given the x. And in terms of math, that means that adapted random variable is the one minimizing this function. And among all the guy z adapted to x. All right. So let me go with proof. Number 1. The conditional expectation random variable is unique. Why is that? Well, how do I show the y star and y twiddle must be the same with the probability 1? In order to do that, so what do I observe? So I observe, well, so 1. Okay, so I want to evaluate the probability of y being, y star, y twiddle. This is by law total probability. Y star being y twiddle, condition on x. Probability of x. Right. This is summation on x. Okay. So because Y star and Y turtle, they both, what? They are both, so things. Y star and Y turtle are both adapted. Adapted to X. So Y star condition on X is equal to constant, so Y star is just a constant. And they have a Y turtle condition on X, the same as the Y turtle condition on X. Just a constant. Alright. Also, what do we have? We have from part B. Part B. Sorry, it's just like addition. So, awesome. So B implies special value of Y. When I guess this is the same as Y star, when I guess same as Y turtle, when I guess. So this is value of Y star, and this one I guess. So really I guess, same thing. Expected value of Y turtle, this one I guess. So really I guess. Implying these two quantities have to be the same. And based on that, based on that observation that we have, that's the same thing as saying so you go back, if you accept that, then you go back to this. This is quantity is always equal to 1, and the rest is just a collection of an exhaustive probability. So sum is equal. That's why you have the sum. Hence, I guess we can say hence. Probability of Y mean Y star mean Y turtle, and summation of that quantity condition on the X, probability of the X. This is equal to 1, and so I have summation on X, probability of my X, but that is just 1. Confirming that the conditional expectation as a random variable is unique. Okay. Now 2. Well, so this is part 2 is pretty much a similar, but then we have unexpected value by identity. So okay, so now 2. 2 is pretty clear because it's straightforward from the definition. condition of v, right? Again, v y 1ax equal to y star 1ax. So that would imply set value of y is 1ax. Set value of y star is 1ax. And as a consequence, expected value of y star is summation of the expected value of y star condition of ax probability of ax. That's here the same thing as expected value of y condition of ax probability of ax, which is the expected value of y. Right? That is also the very well known property that is written in this way. Expected value of y condition of x knows it by expected value, and that is expected value of y. So this is a kind of like a very popular formula for conditional expectation. Okay. So I will try to go as close as I can. If I be able, if I'm not able to cover everything, then just read the note. Okay. So now 3, I want to show those two conditional expectations on the right summing up is equal to the left conditional expectation. And for the second notation, let me denote the following. U star to be U conditional x, and the V star to be V conditional x, right? So in order to show, okay, so I want to show, so I need to show U star plus V star equal to the expected value of U plus V conditional x. Okay. And in order to do that, we just follow the idea from part number 1. So we want to show the U star plus the V star satisfying the conditions A and B. And then by the uniqueness of conditional expectation, these two random variables have to be the same. So in other words, I want to show U star plus V star satisfies A plus B. Okay. So the first thing, so A, how about adaptiveness? So we see that U star, the same as U star and V star both adaptive to X. So the sum has to be adaptive of these two. Because if I tell you the value of X, then I know U star and V star are constants, then the sum is constant. So A is okay, so this is the proper A. Okay. So now, how about the that quantity? So now, so we have expected value of U plus V 1ax, alright? As you can see by the linear combination, that is expected value of U 1ax. plus expected value of b, 1ax. And by the definition of the u star and v star, that is equal to u star 1ax plus expected value of v star 1ax. And then I'll just combine that. I'll just combine. So if I combine them, I have, okay, so that's equal to u star plus v star times 1ax. Alright. So, u star, this quantity, this sum here satisfies the condition A and B. Alright, for the u plus v. So by the uniqueness, so by the uniqueness of conditional expectation, expected conditional expectation of u plus v condition on x has to be equal to u star plus v star. In other words, that is the same thing as u condition on x plus expected value of v condition on x. Yeah. So, for if y is independent of x, then basically it says the best guess for y given x is just the mean of y, basically. So, okay, so I guess this will be the last piece in this. Okay, so now, for, okay, so similarly idea. So I want to show positive value of y, which is a constant, satisfies A and B. Right? If the mean of y at that constant satisfies A and B, then we have the equality number 4. By the uniqueness of conditional expectation. Now, because of course this is constant, so satisfy A. So y here, median a constant. So satisfies A, obviously. And now B. I have y times 1/x. Alright. I want to show this is equal to x. 1/x. Need to show this. How do I show that? What do you think? What I have not used. Which property I have not used. I have not used independence. If y is independent of x. So if y is independent of x, the product is split. Split the value of y. Set the value of 1x by then again, this is a constant. This is a constant, so that could be a plot into this expected value. Right. It's a constant, so I can bring it outside or inside of expected value if I want to. Since expected value y is a constant. So that means this constant, the mean of y satisfies A and B, and so conditional expected value of y conditional on x has to be mean of 1. If y and x are independent. Alright, so let me stop here.